The disclaimer is that today will be a lesson that is completely biased, so it's my view on the different things that we have seen. And in the last part of the talk, I will devote some of the time that I have to show you what I actually do and like to do uh, in this multi-messenger scenario. Okay, so let's start. That's the uh, that's the plan of the talk. Yes, yesterday, yes, of that whole routine, but that's not the first multi-messenger event ever recorded. This one is, and it's even better, I would say. So we are talking about the supernovae 1987. Rate of the expansion of the universe done for the first time with gravitational waves, then the connection of the merger of binary neutron star with the creation of a kilonova that was just present in theory, it was never seen before. And also, the other thing that was possible due to this extensive multi-messenger follow-up that we had was um, the the fact that we have seen we could constrain the equation of state of the neutron star, and that's a key point in this type of discoveries. Okay, so and the other thing that we said yesterday was that even though we have this magnificent event, not only in gravitational wave, but in all the electromagnetic spectrum, unfortunately, the missing link is still the neutrino. So we couldn't find any neutrino coming from that region in the sky that we can associate with the GW 170817. And so remember that this event was 17th of August 2017. Okay, so let's see what happened. What happened just a month after. But first of all, I want to introduce you to this plot. This is a plot that is showing you the distance in megaparsec on the vertical axis and the energy in electron volt in the horizontal one. So as you can see, we have that black part of this plot that is not visible with any counterpart, any electromagnetic counterpart. So the only way to access that part of the plot, so really at a high distance and really high in energy, is to use gravitational waves and neutrinos. As we started to say yesterday, let's briefly go through the creation of the neutrinos. So what you have to do is an accelerator that is powered with gravitational energy, and then a target. The target can be dust, can be radiation, can be the interstellar medium, can be anything. And so when there is this encounter between the proton and the target, that can be the radiation or the dust, you not only produce other protons, electrons, photons, but also pi plus and pi minus and pi zero. So pi plus will decay in neutrino as well, and pi zero will decay in gamma gamma, as we have seen yesterday. What happened to photons? So the photons that interact with CMB photons will produce E plus E minus couple. And so you lose the information of these photons because you don't know how to detect this type of photons. And so you lose the information of the directionality of the source. Okay, so you cannot track back the source that produced that photon. And the same thing goes for charged particles, because they are deflected in the magnetic field from the source to the detector on Earth. And so, of course, you will end up losing that probe. Is it the neutrino the perfect messenger? Well, on paper it is, in the sense that is electrically neutral, is almost zero mass. It doesn't interact much between the formation point and the detection and the location of the detector. But the problem is that you have to build really huge detectors. How big do we have to go? So the biggest background for neutrino detectors are cosmic rays. So there is an order of 10 to 6 in amount of particle that you have to reduce to get to a reasonable number of neutrinos. And so even though you go to the deepest mine that you have on Earth, it's not enough to reduce this cosmic ray background. And so the solution is to go in environment like underwater or under ice, in which you detect the neutrino that traveled from the other side of the Earth, and so you use the Earth as a shield against all particles except neutrinos that can travel unaffected over cosmological distances, and then you see the interaction of the neutrino nearby the detector, for example, when they form a muon, and this muon will travel with a speed that is bigger than the speed of light in the medium, so that can be the water or the ice, producing Cherenkov light, this peculiar blue light that we have seen. We have a network of these detectors around the world, as in the case of the gravitational waves detectors. In this case, these detectors don't share any data, apart from Antares and KM3Net. So Antares, I mentioned it probably yesterday, and it was 2,500 meters under the seawater in the Mediterranean Sea in front of the French coast. It was dismantled last year, but it was in operation between 2008 and 2022, and was the largest Cherenkov detector that we have in the Northern Hemisphere. Then there is KM3Net, that, as we will see, has two different sites. One is nearby the Antares site, and the other one is still underwater, a bit deeper, in front of the Sicilian coast, and is both under construction and taking data. We will see why. Then we have, still in the Northern Hemisphere, in the Lake Baikal, and is upgrade the DVD. So this, the concept is, it's always the same. You have an array of strings that are composed of photomultipliers, and these photomultipliers want to catch the Cherenkov light. So the photons produced from the muon, for example, that we were considering before. And so what happened is that they catch the photons, they register the time and the arrival direction, and what you do is you reconstruct you reconstruct first the muon that produced that Cherenkov cone, and then knowing the angle between the muon and the neutrino in the interaction in the water or in the ice, you can track back the source and so know exactly where this astrophysical neutrino was coming from. And the other detector that we will consider today is IceCube. You will probably heard a lot of it in the next week, but we will see it briefly. And that's a huge detector that is at the South Pole and is taking data since 2008 in the final configuration. Bless you. So let's start with IceCube. This is the location of the IceCube detector, and here at the South Pole, you stand on a few kilometers of ultra high purity of ice. Why is that? Because that snow fallen before the dinosaurs were on Earth. So it's ultra clear, and you cannot even produce it in the laboratory. So it's not really possible. As I was saying, the IceCube detector is composed of 86 strings, and in each of these strings there are these photomultipliers. And you see the detector is deployed between about 2,500 meter and 1,500 meter under the ice. And you see as reference the 300 meters of the Eiffel Tower. And so the total amount of photomultipliers that want to detect the astrophysical neutrino are more than 5,000. And the complete instrumented ice, it's order of 1 kilometer cube. So I want to show you, since both IceCube, Chem3net, and Antares are really in a particular environment, in the sense that is it true that you probably don't have to build something like LSC, but you have to go down. So in the case of IceCube, drill holes that are big enough to deploy the photomultipliers and be able to detect something. And in the case of Chem3net, you have to deploy in the deep water these kind of strings. So how did they solve the issue? To dig something that is so deep, in the first few 100 meters, you go with a normal drill, and then this one is an hot water pump that is pumping hot water under pressure, and so you can go through this super clean ice and make the hole that you need. Of course, there are many people working there. This is all the amount of things that you need, and it takes about 2 days to drill a single hole in which you have to deploy the string with the photomultipliers. And now you will see in a second, first the storage in which these photomultipliers are, that are big and they are looking down because you want to catch the neutrino coming from the opposite direction from the opposite sky. So this is the drill, the pump drill that is coming out, and now you will see that they will start introducing the photomultipliers. And once you have done, so you finish with the last photomultiplier of the line, then it will freeze again, and you will not see the detector anymore. So if something happened, you cannot go there and change anything. It's there, done. Okay? So this is the storage in which they put in line the different photomultipliers, and that's the process of the deployment. So you deploy one by one. You see everything is coded with the QR code, so you know exactly which is the photomultiplier that is in a particular position. What about ChemTreeNet? ChemTreeNet decided to have two different sites. One, as I was telling you, is nearby the Antares site and is 2,500 meters under the seawater, and it's called ORCA, that stands for Oscillation Research with Cosmic in the Abyss. The other one instead is here, in front of Porto Palo, and is ARCA, and is 3,500 meters almost in the deep, and it's called ARCA and stands for Astroparticle Research with Cosmic in the Abyss. Why do we have two different sites? Because the physics that we want to do is different. So in the case of ARCA, we want to detect high energy astrophysical neutrinos. When I say high energy, it means energy bigger than TeV energies, okay? In the case of ORCA, you will see that the composition of the ray is similar, but the detector is denser. Why is denser? Because the aim is to detect the neutrino oscillation, and so you need the photomultiplier to be closer to each other. So for the ARCA configuration, in the final configuration, we will have two building blocks, each of 115 strings, and you see this one is a string. The difference between the photomultipliers that we have seen, the single big photomultipliers that we have seen in the case of ice cube, is that here, I don't know if you can appreciate it, but there are several smaller photomultipliers. To be precise, they are 31, and that's because is it true that you want to look for upward going events, but then you have also to discriminate in case there is a fish that is blinking light, and so in that case that will be the glitch that you want to remove. The angular resolution is 0.2 degree, and you see the vertical spacing between the photomultiplier in the case of ARCA is 36 meters, and the horizontal, so between one line and the other, is 90 meters. So it's really a sparse building block. And that will be, it will have, in the final configuration, will be with a similar sensitivity of ice cube. But now we see the sky pattern. This is ORCA. You see, is a denser detector. Is one block, building block, so it's only 150 strings. The vertical spacing, instead of being 36 meters, is only 9 meters, and the horizontal one is 23 meters. And the configuration, of course, of the optical module is exactly the same. Okay, here is this slide is to give you an idea of the proportion of the instrumented volume that each of these detector has. So here you have as a reference Super Caniocande that was operating for 25 years, Antares that operated for 14 days. So ORCA will be a bit smaller than the Antares detector that was dismantled, and ARCA will be of the dimension of ice cube and even a bit bigger. Do you remember when I show you the antenna pattern? And so the visibility sky that we have with the gravitational wave. Also with this detector, is important to have a complementarity. So the fact that there is one detector that is in the northern hemisphere, that is ChemTreeNet, and the other one at the South Pole that is looking at the opposite side of the sky, is fundamental, because not only you have a complementarity in the sky, but you have a region of the galactic plane that is in common. And so that's the region in which there are a lot of sources that are interesting to detect, and so it's important to have the two detectors with a similar sensitivity in the different hemispheres. And so you see, this is the part at which this is ice cube. This one is the part at which ice cube is blind, so it's not sensitive, and the same here for Arca. And so when you mix them together, there is a common region over here that is particular fundamentally for astrophysics. So I show you the deployment in IceCube. I want to show you something similar for Chem3Net. So in the case of Chem3Net, you don't have to drill anything, but you have to take a ship, you have to go there, be ready to deploy your strings, and you have to have sea condition that allow you to do this this complicated deployment. So the thing that you see here, I don't know, yeah, that you see here is a sphere that we call launcher, because the string is inside this launcher. And what happens is that a robot fixes the connection of the street at the bottom of the sea, and then there is an acoustic signal from the ship that it will allow the release of the string. How is possible? It's like a yo-yo in the opposite direction, in the sense that the launcher, it will unfurl and so release the string, and then you will have the vertical string that is attached to the base of the sea, and you will collect back the empty launcher for the next use. Now I will show you a brief. So this is the unfurling mechanism in which the photomultipliers of the strings are released, and then you collect the launcher. Usually this is possible during a week or 10 days of deployment, depending on the weather condition. So this one here is the so-called junction box. That is the one of the key part of the instrument, at which you, if you can see these orange connectors, is where the robot connects each of the strings, and is the one that is connected to the offshore laboratory to obtain the data from the detector. And so you see, it's a long process. It's just one piece, but that has to arrive to 3,500 meters. So what I'm showing you is just the first part, in which they just put it into the sea, but then has to arrive down. And it takes a bit. I mean, it's a patient work and has to be extremely delicate. Okay? I want to show you if... of course not. Hello. Okay. Let's see. Maybe this works. Okay, so that's the first part, in which there is the unfurling of the launcher. I find it really interesting when I saw it the first time. Okay. Of course, it's the first part in which there are the lights of the robot, otherwise it's completely dark and you cannot follow it till the sea level. Okay, so what is the status? The status of Chem3Net is in construction, but is already taking data. The effective instrumented volume is already bigger than the one of Antares. We will have a deployment in September to deploy 10 string more. So we are growing faster, and we should be able for the end of this decade to have the first building block in place, so 115 strings. So this is the interaction that I was telling you about. So it's the neutrino coming from the other part of the sky using the Earth as a shield, so that the neutrino can interact in the vicinity of the detector, producing a muon in this case, that will travel, produce the Cherenkov light that is the one that we want to detect. So this is, if it works, it's a nightmare. Okay. So you see, this is the Cherenkov cone, and this is and what you see on each of these strings, in this case is ice cube, what you see are these sphere. So the color is time in the sense that it goes from yellow to purple, and bigger is the sphere that you see, bigger is the number of photons that have been detected. The first evidence for neutrino was related to diffuse flux. And so IceCube already 10 years ago, 2013, detected 28 events. These events were pretty peculiar in the sense that they've been detected at really high energies. The one that you see here are the most famous, Bert and Ernie. Let's see if I can, I can show you one. Okay, so what you see is the detector that is catching the Cherenkov light coming from the muon. And you see more than 300 optical sensors were involved, more than 100,000 photons in just a small amount of time. If you see something like that, you don't realize how big is this event. Let's try to superimpose this event to the headquarters of IceCube that is in Madison, so a regular US city, okay? And that's what happened. This is just half of the event, okay? And so if you're carefully counting the blocks, it's about 12 blocks at least of a US city. So it's a huge event in space. And maybe you notice that each of these events has a name. Why is that? Studies show that if you connect the characteristic of an event with a name, it's easier to remember. And in particular, they choose puppet names. So it's something that probably everybody of us know, and so you can recollect that the first two were Bert and Ernie, and then you have the other, so Beaker, Kermit, and so on, and these are the other 14 events. Okay, so you remember that yesterday we speak for a big amount of time about the GW170817. So 17 of August 2017. What happened almost a bit more than a month later? September 22nd, 2017. There was a GCN trigger released from IceCube in which they detected a neutrino with these characteristics. So you can see the right ascension, the declination, the error associated with it, the energy. So you have exactly not only the energy in the neutrino detector, but also the position in the sky. And so, of course, everybody was trying to follow up the event and to find a correlation with the event. And so this is the event, the muon track, the reconstructed muon track. And you see the time goes from the red to the blue, so it's going in this direction. And there was a huge follow-up campaign that took several detectors, not only on Earth, but also in space. And the most interesting thing was that just a few minutes later, both Fermi and Magic identified flaring source in the same exact location. And you see the accuracy of this detector is really great, 0.1 degree. So nothing in comparison with the error region that we have seen yesterday for the gravitational wave events. So this blazar, flaring blazar, is known as Texas 0506 plus 056. We have seen it, Alicia talked about it yesterday. And so the discovery, so the connection between the gamma rays and the neutrinos allowed us to see the complete spectrum of this blazar. And so to connect the archival data that are the one that you see in gray here, that produce the first bump, to the other part of the spectrum that is pointing to a double bump spectrum of this flaring blazar. So that means that this source during the time is emitting and release a huge amount of energy. But that gave us the possibility to study even better this source, just because we couldn't see from a different perspective, okay? Was this source known before? For the optical telescope, yes, it was a known blazar. In the case of the neutrino, IceCube didn't see it before, but what they've done, since they had years of data, they went back and see if they could find any excess of astrophysical origin in that direction in the sky. And actually, they found 10 more neutrinos in the exact direction of these flaring blazars. And so you see, this is the cumulative event over several years, and the evidence for this, the statistical evidence is 3.5 sigma. So it's good, but not enough to claim a detection. What else did they see? So in 2020, this one, this cluster, this galaxy NGC 1068 was one of the significant position in the sky seen by neutrinos from IceCube. And you see, again, is we are getting there, but we are not there yet. So this, the probability associated with this kind of detection is only 2.9, only. I mean, to arrive there, it's a huge effort. They are doing the next step. The evidence, so this was 2020, and they released another paper last year in which you see here is the number of events over the angle, the square of the angle. And so as yesterday we see the background of the gravitational wave and the event, the GW150914, and there was an outlier because it was far away from the distribution of the background. Here is exactly the same concept. So what you have here is on the vertical axis the number of neutrinos, on the horizontal one you have an angle, but what you have to pay attention at is the distribution of the background, that is the orange one, and the data. You see, there is they stick out from the background. So there is an evidence of something. And this evidence has a significance of 4.2 sigma. So we are already almost there, okay? Okay, so this is to tell you that, of course, there is a huge effort in astroparticle community, not only to detect the probe, so the neutrino, the gravitational wave, and the gamma, but also a common effort to try to detect the same source with the different probes. Because that's key to understand the central engine of every astrophysical source. So this detector, of course, Chem3Net is under construction. IceCube will undergo a phase of upgrades. And so this is the scheme of the several upgrades they want to make. They will add radio detector around the place in which is located IceCube. Then they will make a denser array that is called IceCube Gen 2, with the addition also of some optical elements. And so in this way, they will be able not only to detect neutrino, but also to get the interferon photons and radio emission, okay? These are just a few projections. So in the case of the upgrade of the denser detector, you see this is the blazar that we were talking about a second ago, that has a significance of 3.5 sigma, and that will arrive to more than 10 sigma when IceCube Gen 2 will be in operation. And the same over hundreds of days. And the same will happen for the source, the second one I was telling you about, NGC 1068, that is 4.2 at the moment, 4.2 sigma. And so it will arrive to 10 sigma with the new generation, with the new instrument of Gen 2. Okay, so as in the case of IceCube, also Chem3Net has a multi-messenger program, and so it's extremely important not only to be able to reconstruct online the events that you are seeing, so with a latency that is a latency of few seconds, but also be able, when you reconstruct something that you realize is of astrophysical origin, to send out the GCN and alert all the community to follow up that event in a particular place. And so that's the ongoing effort that has been going in my group right now. I want to finish this part of the presentation connecting to what Alicia was saying yesterday, related to the recent case of the GRB 221009. Of course, that was the brightest long GRB that we ever saw. And as all the other observatory, also Chem3Net was doing the follow-up of this event that LASO detected up to 18 TeV. And so you see, here there is on the bottom right, there is this plot that is the position of the source, so declination over right ascension. The red cross that you see is the actual position of the source, and this one is the search area in which we wanted to find a candidate in the case of the Chem3Net. Unfortunately, there wasn't any connection with a neutrino that we detected. The closest one was here. And so, as in the case of the gravitational wave events, you may find correlation in time, but not necessarily in space. And so that's still the missing link. Okay. Since we are talking about the in-stream environment and multi-messenger analysis, I like to remind people that in the case of Antares already, but is ongoing also for Chem3Net, the diversity of the biolife that we have deep in the sea is so huge that we were able to see the passage of these mammals that they weren't supposed to be there. And so also in this case, in the position of the detector was key to hear, because the other thing that I didn't mention it, but the other thing that we have in the detector are acoustic sensors. So you really hear the clapping of the dolphin, where they go, how far they go, and how they are affected by the traffic of the ship and the naval environment. And so this is another case in which a detector that is done to do completely other stuff, so to look for astrophysical neutrinos, can have an impact on biology, or on the study on the current, for example, because to be able to have a detector that has the strings that have to be vertical, and if not, you have to correct your data analysis related to the current that was there that day at that velocity. You can do a lot of studies using different information coming from different instruments. Okay. So now, in the remaining time, please allow me to show you what I like to do. I think the future is, and I said at the beginning that a completely biased lecture. The future is in supernovae. This is SNU is an early warning system in which we want to get the trigger of the neutrino event in time to follow up the astrophysical source that produced that event. And so there is this global effort in the astronomical community to have not only the neutrino alert, but to have a follow-up campaign for this type of triggers. So as you know, we have about 1 supernova per second in the universe. And if we go down to our Milky Way, it should be order of 1 every 30, 50 years, okay? Broadly speaking, we can divide this supernova in 2 different types, type 1 and type 2. The type 1 is the so-called thermonuclear supernovae, and the type 2 is the core collapse supernovae. So in the first case, you have a runaway thermonuclear burning white dwarf, and these kind of sources are really bright. That's the reason why they are used as a standard candles. They don't leave anything behind, so there is no remnant, and the amount of energy that is released is order of 10 to 51 erg. In the case of the core collapse, so that can be type 2, 1b, or C, you see the luminosity curve has different characteristics in comparison with the type 1, and that's the result of the collapse of an iron core of a massive star that can be a mass from 8 solar masses to 100 of solar masses. The remnant is either a black hole or a neutron star. The energy release, it's order of 10 to few times 10 to 53 erg, and that energy goes 99% radiated into neutrinos. So let's consider this case, so the case of the core collapse. So we said we are considering the collapse of a massive star. As you know, a massive star spends the majority of its time burning hydrogen, and so the helium that is produced then will settle down, and when the temperature will be high enough, it will burn and produce carbon, and so on. So the process goes till iron, that is the most tided bond nuclei. And you see, if you take a look at the time scale, effectively I took the case of a 25 solar mass star. It spends 7 million years burning hydrogen. Okay, so really the majority of its lifetime. So what happened when you arrive to iron? The iron core is supported by the electron degeneracy pressure. And so when the radiation pressure is not balanced anymore by gravity, the collapse starts. So just before the collapse, you have this onion shell structure of the star. And of course, we said that all these shells are not other than the ashes of the previous sequence that was the burning stage. And so when gravity doesn't balance anymore the radiation pressure, we have the collapse of the star. This collapse stops immediately when the nuclear saturation density is reached at the center of the star. And so what you have is the so-called proton-neutron star. At the same time, what you have is that the newly formed shock bounces back, and so you have this new shock that is propagating both in mass and radius over the extension of the astrophysical sources. And then there is a moment in which that is called a stagnation, in which we are not sure what's going on. And what happens after is that when there is this shock that is propagating, the neutrino, so the emission of the neutrino carries away the energy, the 99% energy that we were talking about before, from the post-shock layer of the star. And so the explosion of the star will happen only if the heating by the neutrino is strong enough. In that case, the shock can be released and go outwards, and we will have the explosion of the astrophysical object. And so there is the explosion and the nucleosynthesis of all the elements that have been created along the way. Isn't it impressive? I find it really interesting. So what's the problem? The problem is that what I explained to you is the so-called neutrino-driven mechanism for the collapse of a supernova. And as we have seen, there is both the emission of the neutrinos in radiation from the post-shock layer of the source, but also inside the inner core there is the production of gravitational waves. And so even though these explosions are one of the most energetic in the universe, in terms of gravitational wave, we expect a signal that is faint in the actual detectors. And so we need to find out, so it's order of 10 to minus 23 in strain, in perturbation. And so the point is that we need to find out better ways, new ways to increase not only the volume of the universe at which we are sensitive, but also the possibility of our detector to be sensitive to such faint signal. And so the idea is to use better performing statistics. So in the rest of the talk, I will explain to you what we have done and what we are actually doing with the new data. So the interesting, okay. So since we don't know what waveform to expect in gravitational waves is not like a binary system that we know everything of it. This signal is stochastic in the sense that we don't know the exact shape that we will have in our detector. And so when there is a huge effort to create core collapse supernova simulation to know what this signal will look like in gravitational waves. One of the issues is the computational power. You have to have almost infinite number of computers to run this simulation on, because these are, especially this one that we are seeing, are like 9 months simulation. So you send your computer, you send your code to the supercluster, and after a bit of time, you will end up with what you want to see. And I find extremely interesting the fact that different groups around the world, the leading groups are in Japan, US, and Germany, find out that with different assumptions, we will see that creating the code to produce this type of simulation is not trivial, in the sense that it's not only general relativity or transport emission or fluidodynamics. It's a mix of all these different physics ingredients. So when these different groups produce a common result, I think is extremely important to look at it and find out how to use that information to look for the signal that you want to detect. So in this case, this is taken by this paper. What they've done, they simulated the collapse of 11 solar mass with different equation of state. So on the left, you see the softer equation of state, and on the right, you see the stiffer equation of state. But what is remarkable is the fact that for gravitational wave, in the time frequency plot, they find the same structure in the signal. So what you have, even though the equation of state is different, so you are implying different mechanism and the variation in the parameter space that you are using, what you find is that the common feature is this arc shape. So that's the description of the excitation of the G mode on the proton-neutron star. So this is the common one, and this is this blob that is tagged as B is called standing accretion shock instability, and is due to the convective layers that are outside the proton-neutron star. And so you see, we have, with different equation of state, we have a common feature that we can look at, and another one that is not common. So if we get to see the second one, we know that the equation of state would be softer. If we get to see both, we know for sure that it's softer. If we see only one, it can be either of the two, okay? So I show you the different simulations. So again, on the left, you see the softer equation of state. On the right, you see the stiffer one. What is different is this production. And so at a certain point here, you will see a sloshy motion of the convective layers that is really remarkable, in the sense that it will be extremely evident in the simulation, and that's exactly what produced this SASI, that is the standing accretion shock instability. You see, is this motion of the convective layer that is producing this feature at this lower frequency here. Okay, so till now we said that not only the core collapse releases neutrinos and gravitational waves, we can have a way to discriminate the different modes of the protoneutron star. And even better, there is for the SASI, so the shock accretion shock instability, that there is a relation between the neutrino and the gravitational wave signal in the frequency. So the frequency of the neutrinos is half the frequency of the gravitational wave. So if we cannot only nail down the type of signature that we see in the time frequency plot, but we can also connect the two different probes with the same information, frequency. Okay? Okay. Okay, so what are the two different scenarios? There is the neutrino-driven core collapse, that was the one I was showing you before, and there is the rapidly rotating scenario one, that is the magneto-rotationally driven. So according to theoretician, the first scenario is the 99% of the cases, and the magneto-rotational one, that is the one that should give us a better signal, unfortunately is 1% of the cases. Okay, so let's see what are the different that we should note in the time frequency plot. So you see that in the case of the neutrino-driven core collapse, what you have in the time frequency plot is the prompt emission, that should be the emission of the neutrino, so the one that will trigger the follow-up of the other experiment. And then you will have, see, the G modes, so the arc shape that we have seen in the previous plots, that is due to the modes at the surface of the protoneutron star, and this one that is the SASI. So exactly the same schematics, that sketch that we have seen in the simulation. What happened in the case of the rapidly rotating scenario? In this case, it's even more complicated to have a clear signature, because what you can have is the merger of the two. So you can have a signature that is not, that is both part due to the excitation of the G modes, so this arc structure, and the other part is the standing accretion shock instability. And so it will be even more complicated to disentangle the two components. As I was saying before, getting the supernova explosion model is not easy at all. You see, these are just few of the ingredients that you have to put in place to have a model to construct the signal of a core collapse supernova in gravitational waves. So they go from general relativity to neutrinos, to the nucleosynthesis, to the hydrodynamics, to the neutrino physics, and so on. So it's really a huge variety of physics fields and also ingredients that you have to insert in your simulation. So since we don't have infinite power, computing power, what we decided to do was to use what we call the phenomenological waveforms. So what we do actually is to mimic the behavior of the signal that we should expect, so the raising arch in the time frequency plot and the SASI, with something that is more manageable. So it doesn't need months to run on a supercomputer. And so the idea in the construction of these phenomenological waves is the fact that every perturbation of the protoneutron star will excite the IM modes. And so we will have, in particular, the excitation of the G modes, and considering the convective layers, we will also have the instability due to, that is the one that produced the SASI feature. So this is how phenomenological waveform looks like. So again, this is the frequency over time. Here you have the corresponding strain over time of the signal. And so you see what we are trying to produce is exactly the characteristic excitation of the G modes, so the evolution of the protoneutron star that you see. This is the parameter space that we are using right now, and you see new and flexible in comparison with the previous type of waveform. So every time that you do an analysis, then you refine different characteristics and try to be better. And the other things that we introduced in this case was the distance of this source as a parameter, because it's the only way to compare the detection horizon, if you want, that you are sensible to with the other analyses that are ongoing. Okay, so what's the strategy? The strategy is the following. You create a huge set of time frequency plot to feed a machine learning algorithm that will analyze the data and give you the classification of the image as signal or noise. What we are using, the result I will show you are related to the O2 data taking. So if you remember, in that case, what we had were the two LIGO detectors and the Virgo detector. We have taken the amount of coincident time in which we can have the three detectors. So it was the last month of the O2 data. Kagra was in action. You know better than me what is machine learning. Probably you use it every single day. Actually, we do, and we don't even realize it. So it's widely used in every kind of situation, from customizing of the program, Netflix, Prime, whatever you prefer, Amazon, or database mining and so on. What I like to remind is that a computer program is set to learn from experience with respect to some task and then perform measurement. So if for example, the code has to learn how to win a checker game, the experience will be the fact that the program plays thousands of game itself. The task is to learn how to play, and the performance measurement is the probability of winning, okay, to be successful in that checkerboard. Okay, of course you have thousands of different variation of the same machine learning algorithm. You can classify things, so you can denoise, so you can find the structure into the data that you want to see. In our case, we choose the neural network that is, to be precise, a convolutional neural network. And so what it does is to update gradient descent algorithm and minimize the cost function. And so why is so close to us? Because this type of algorithm was biological driven, and so what it does is it's exactly what your brain does for you every single second. In fact, you have the eye, that is your optical system, that creates the upside down image on the retina. Then the retina sends the and convert in light inputs the signal to the brain, and the brain is the one that elaborates the data and gives you the final image. And that's exactly the same process that the convolutional neural network wants to apply. So you start from pixel, you look at the ages of the image, then you look for an object part, and then you will have the complete object discriminated. Okay, it is important, how we said, to train and test the algorithm. The training part is to allow the algorithm to learn what you want to teach. So in our case, we want to find the signal rule of the goal collapse, and then you have to test the algorithm against something that you never see before. And so in all this, what you do is you construct a confusion matrix with the positive and negative rate of the probability that you want to detect. All right, so that's a general workflow. So what you do is to you feed the algorithm with a certain test set. The test set is divided in two. One part is for the training and the other part is for the validation. And then what you do is to try to optimize the performance of your code, and then to estimate the model. What you have to do is to evaluate the detection on the unseen data that is our test set. So how does it apply to our case? We want just to discriminate between signal and noise, but we need to reconstruct almost perfectly the signature that we want. So the G modes and the SASI in the time frequency plot in the gravitational wave analysis. And so to do that, we not only produce a huge amount of phenomenological waveform in the time frequency plot, but we also use a GRB multi-detector scalogram that is the following. So what you do, you have, in our case, you have 3 detectors. You assign a color to each of these detectors. So in the case of M4 is red, for example, Livingston is green, and Virgo is blue. And what you have is that for each detector, you have the time frequency. Then what you do is you try to find the coincidence between the detectors. How do you find the coincidence? With colors. If you have the signal that is visible in Hanford and in Livingston, the feature, in this case, the arch structure of the G mode will appear in yellow, as in this case is yellowish because only Hanford and Livingston have a signal. Otherwise will be a correlation of the signal that have been seen between M4 that is red and Virgo that is blue, so it will be this violet and so on. If all the 3 detectors detect, so see the signal, you will have the signal ending up in the cumulative time frequency plot in white. So to show you the difference between only noise and signal plus noise, this is how the time frequency plot, the pixel one, looks like. So here, of course, you can see the signal by eye, but it's not always the case. Usually what we do is to dig into the noise. So it's having a signal like that, it will be impressive. Tell me where do I have to sign, because I do. Okay, so in our case, the structure of the deep learning algorithm trains a number of parameters that is order of 99,000, and it's a rather complicated network, but the task is a 2-class problem. So we have to distinguish between signal and signal plus noise. Here I put some information about the amount of time that you have to run your code. So the training and the validation phase took about a couple of hours on a GPU, and the prediction is done in 3 milliseconds for each segment of 2 seconds long image. What are the numbers are talking about? So in the previous, of course, we check with the Gaussian noise, that is the ideal case, but not the reality. In the real noise, what we had done was to construct a training set of 70,000 images with the phenomenological waveforms in a different range of distance between 0, 2, and 3 kiloparsec. 75% of this test set, of this training set, were used for training, and the 25% were used for validation. Then we produce what we call a blind set that is not involved in any training or validation procedure. Is just a set that we use to see how good is the process that we are doing. It will be clear in a second, and it's composed of 260,000 images with random distances and a uniform distribution between 0, 2, and 15 kiloparsec. So when you train and validate your network, then you have to face the real world. What is the real world in our case? In our case is use the simulated waveforms coming from the literature, so the one that I was showing you with the movies before, to see if we are actually able to detect something after this long process of training and validation and test. I have also to add that for the noise budget, what is usually done is to take the noise, some noise days, and shifting these days in data is like when you scramble data, in the sense that they don't have any time connection anymore, and so you are sure that you can produce a longer amount of stretch of data, and in this case was 2 years of time shifted data to test on the noise class. So the output of the network is a probability vector, theta, and that contains the probability of the event to be associated with the noise class or with the event class. What you do during this process is to set a decision threshold, theta star, and so if the probability theta overcomes this theta star, then the candidate is classified as event, so as a signal. Otherwise, it's noise. And this is the confusion matrix that we have seen before. And so what we also use is the efficiency, that is the ratio between the correctly classified signals over the all signals that you input in the data, and the false alarm rate. So we will see that you want to maximize the efficiency, but you have also to minimize the false alarm rate. And so there is a balance that you have to have in your decision. This plot is a comparison with the previous work. So the previous work is shown in dashed line. So here the vertical axis on the left is the efficiency, and the one on the right is the false alarm, and the horizontal axis is signal to noise ratio. So what this plot is telling you is that you want to maximize the efficiency. So you want to have 100% efficiency, but at the same time, you want to have a false alarm rate that is the minimal possible. So in the case of the previous work, this was the efficiency was about 90%, and the false alarm rate was order of 3%. In this case, we could do even better, introducing the so-called binary cross entropy. So we choose to insert in this training and validation a weight. A weight equal 2 in our case means that it is 2 times more important to correctly classify noise rather than have an event. So we really don't want to have spurious event. We don't want to have in the data something that is flagged like an event, but it's something else, okay? This is coming out from it's a snapshot from the validation process. And again, what you see is that the efficiency, this is network SNR. So we have 3 detectors. If we consider them at the same level, in the sense that they act exactly in the same way, having an SNR, a network SNR of 16 means that for each detector you have to divide by square root of 3. So you have something on the line of 8 for each detector, okay? And so you have to maximize the efficiency and minimize the false alarm rate, as we said. This is to show you that the decision threshold, the theta star, that we choose as 65% was a robust choice because when you plot the probability density over theta, that is this decision, what you have, you want to discard the majority of noise as you can, and you want to keep the majority of signal in the right direction. So in this case, the real detector noise are the green bar, while the signal are the light blue one. So taking the theta star at 65% means that we can discard more than 98% of the more than 99% actually of the background, and keep the signal as it is. And these are a couple of results. So this is the efficiency over distance. So you see, you can going farther means that you're losing in sensitivity, but we are able to detect something with 60% probability also at a distance of 15 kiloparsec. And the same result, you can see it as function of SNR. So how big the SNR has to be in the network of the detectors to see such an event. Okay, so I want to finish with this. So we have seen that it's possible to see and to look for your favorite source or whatever you want to find in the universe in different multi-wavelength, in different wavelength. So it's the so-called multi-wavelength. And if we put everything together, so not only visible light, hydrogen alpha, that's the microwave, gamma ray, radio, CMB, and gravitational waves, we hope to have also a neutrino sky that is visible as this one. We can really have a bright future ahead of us. So that's the last slide. Thank you. I will take questions.
Hello, thank you so much for your lecture. I have learned so much over those last days. And I have 2 questions. One about the IceCube blind spots, because IceCube is meant to see neutrinos from the other side of from the other side of the Earth,
yeah,
right?
So the northern sky.
Yeah,
yeah.
But neutrinos barely interact. How do we have like blind spots for neutrinos? Like, couldn't we see? I don't know, that might be a naive question, but like, can we see neutrinos from everywhere? How can we separate where they're coming from?
Okay, it depends from the location of the source. So you can have neutrinos. I didn't speak about the background of such kind of detectors, but what you have is not only cosmic rays that you reduce going deep into the ice and into the ocean, but you also have atmospheric neutrinos that they can again travel unaffected, but they are not of astrophysical origin. And so to distinguish between the atmospheric neutrinos and the astrophysical one, you have a different power law at which these events are produced. So that's the discrimination factor. And considering the sky map that I show you, that depends on the position of the detector. So is it true that you are in the case of ice cube, the northern hemisphere is the one visible, but you have preferential direction in which you are most sensitive to, like in the case of gravitational waves and some other detectors like this. I would like to find the slides.
Okay.
Oh, this one, yeah. Attento. Careful.
Thank you for the wonderful lecture. I also have a question regarding the ice cube. So you have mentioned many pictures detected by the ice cube events. So could you please tell me about what kind of neutrino flavor they are? So does they leave same kind of like pattern in the detector, or?
So if I remember correctly, is muon neutrinos.
Okay, so
yeah.
Does they leave same kind of pattern in the detector, or like electron neutrino leaves different kind of pattern in the detector, or muon and tau, they have different kind of. How to distinguish like?
From the okay. How do you distinguish the different flavors?
Yes.
So since they interact in a different way, you have a different track that you can reconstruct in the detector, and so each of the track points you to the different flavor of neutrinos.
Okay.
I can find out this slide and show you the different maybe later on in the break.
Thank you.
So about the deep learning architectures and the training models, so do you think it's possible to use that model on the real-time analyze, or that is just used for data processing posteriori?
No, the idea is exactly that one. So the when we have we are absolutely sure that this code is revised through the collaboration, and we prove that it's effective. The idea is to put it online and run it online. Yeah.
Thank you for for the presentation. Regarding the simulations of neutrino core collapse during supernova, well, the mass of neutrino is not well constrained, right? So I suppose that in those kinds of simulations you use it as a parameter. So I was wondering whether how sensitive is the output of those kinds of simulations, so that would it be possible to constrain neutrino mass through observations comparing with
okay, that's a good question. So the simulation that I showed you are related to describing what is going on in the core collapse with the aim of gain the structure of the gravitational wave. So is it true that they use the neutrino mass in a certain range? But I don't think that with this type of simulation you can constrain the mass. You need another type of experiment to do that. For example, Orca can do that if we will have a really precise measurement. Other than the oscillation order, we can also give information about the mass.
Oh, thanks. Well, it was not clear to me if currently you expect signals from core collapse supernova in gravitational waves.
How often? What's the question?
No, are you currently expecting a gravitational wave signal?
Yeah.
Okay.
That would be great.
Okay.
Not 6.4 megaparsec as the trigger of a few days ago, because it's out of our reach, but yeah.
Thanks.
if it's close by, I hope we will see it.
I don't really understand why you have blind spots for the neutrino detectors. Like, wouldn't you have a neutrino come from above and interact inside the detector, and you could see it? I don't know.
So a neutrino from above, so if this is ice cube and a neutrino is coming in this direction, is background for ice cube. So what you want to detect are neutrino coming from the opposite part. Okay,
And that's
so
why it's background. You can reconcile.
because in that way, so in that way you can discriminate the astrophysical neutrinos that are not they are not embedded in the cosmic ray background. That's why you use the Earth as a shield against all particles except the neutrinos. The fact, so the position of the blind spot is due to, again, the location of the detector. So it's not really related to the particular interaction. Of course, these are really sensitive detectors, but the point is that there are some position in the sky at which you are not really sensitive, and so that's or you have a reduced sensitivity. So call it blind spot, probably is it too much, but it's just to let you understand that the visibility in that case it's problematic, and that's connected, for example, to the case of the GW170817, in which the event was out of the horizon for ice cube for a few degrees, and it was in the Antares horizon, but at that point the sensitivity was not enough. And so if you have an event that lies exactly in that part of the sky, it's almost impossible to say we detect something, to claim a detection.
So we cannot discriminate muon neutrinos from muon generated from neutrinos from muon generated from.
No, you can discriminate. You can discriminate because your detector works, but you don't have an high efficiency to do that. So you arrive to 2.9 sigma, 3 sigma, okay? The best possible scenario will be to have a source, a common source in the galactic plane, exactly in the area that is common for the two detectors. And so in that case, we have a beautiful event to be detected.
Okay, thank you.